Okay, so aside from this, let us now move on to another classification, which is the what we call the multidimensional heat transfer. Actually, we have uh, heat transfer problems that are classified in terms of the number of dimensions from which heat flows occur. Okay, so in here we will gonna tackle the different dimensions on where our heat transfer or the heat flows occur. Okay, so basically our most general case heat transfer through a medium is how many dimensional number? So we have three-dimensional. Okay, three-dimensional. But in some cases, under the simplifications and assumptions, of course, heat transfer may reduce to one or even two dimensions, or one-dimensional or two-dimensional, which or wherein we may simplify our mathematics. Okay, so for example, if there is a perfect insulation in I mean in y and z axis, or in y and z direction of flow, then we can now assume, or we can now use the assumption that our heat transfer is in terms of one-dimensional only. So as an illustration, like what I have said, in reality we have a 3D, three-dimensional. Say this is our medium, right? Say we have so our medium is in 3D, or three-dimensional. So we have along x, along y, and along z direction. So say this is our x along x direction. Say this is our along x direction, this part here. This is our x direction, and this is our y direction, and say this is our z direction. Right? Okay, so in reality, this actually occurs in x, y, and z direction, right? Okay, but like what I have said, for the simplification and for simplifying the mathematics, especially when the 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 heat transfer uh, under some cases have a the what we call the perfect insulation in one of its side, then we can now simplify our our uh, our our heat transfer in these different dimensions. So say this is our 3D, then we have the 2D, so we have same illustration, and we have our 1D. Okay, so once again, we have this multi-dimensional heat transfer. This first figure here is a three-dimensional, meaning our heat flows at x, y, and z direction. Okay, so in reality, we have this case. Okay, but in some simplification, we may limit our calculation in either in 2D or even 1D. So in 2D, we have the flow uh, either of the two, either in the two directions, x and y and z, z and x, and so on. Okay, and our assumption here is that if we can say for example that if there is a perfect insulation, say we have a perfect insulation of this part here. Okay, so if we have a this is a perfectly insulated part, then uh, as you can see, there is almost no QX, right? Because this is a perfectly insulated material, or this is where it has a perfect insulation. Okay, that's why we can simplify this problem with only considering the flow that occur to x and y direction. Okay, so the same goes with the um, the 1D. If we have this part a perfectly insulated material, or we have a perfect insulation, and also this part as having a perfect insulation, then we can now observe our flow only in one direction, okay, going to this x direction. And by having this condition, then we can now adapt, or we can now say that we can use or simplify our problem using 1D only, right? Also, whenever we talk about dimensions, we have talked this different dimensions, we can relate this to a coordinate system. So our example here, the 3D, 2D, and 1D illustrations here is um, described by the what by the what we call the rectangular coordinate system. And remember, we do not only have rectangular coordinate system, but we have also other coordinates system like the cylindrical and spherical. So we can also use that coordinate system. Okay, let's write here uh, the cylindrical. Oops, that is letter L. Cylindrical and the spherical coordinate system. Okay. So aside from this rectangular coordinate system, we can also express our uh, dimensions using these two cylindrical. These other two coordinate systems. So let me have an illustration using, say, let me illustrate this first, the cylindrical coordinate system. Okay, so I have here now the illustration of the cylindrical coordinate system. And to locate a certain point, say we have this P. It is now a function of our radius. This is our R, or this part here. and the uh, the uh, the angle between this, or the theta. So we have P, R, the theta, and of course the uh, our L, right? This part here, our L. And okay, so this is our cylindrical coordinate system. Okay, so to locate this point P, so we need the R, its radius, the theta, the angle between the R, and the L, or the longitudinal direction of this cylinder. Okay, and let us compare this to the rectangular coordinate system. Say we have also like this, the x, the y, and the z component. So to locate our, say this is our rectangular right, so it will looks like this. So if you're gonna locate this point P here, then what we need is to have our x, this our x, I mean this is y and this is z, the y and the z, right? That is our points. Okay, and lastly, using the spherical coordinate system, so we have something like this. So spherical, we have, say this is our coordinates, and we have a sphere. Say this is our sphere. Excuse me for my drawing. So to locate a certain point P, what we need is the of course the R, the angle between these two, say this is theta, and the angle from here. Okay, so this angle here is what we call phi. Okay, so we need these three. So the R, the angle, and this another angle, which is phi. Okay. So that is our three coordinate system.